Good morning, class. Today what I wanted to do is I wanted to run you guys through the difference between differential equations and algebraic equations. Okay, now these two pop up a lot in SCIE1000, so it is important for you guys to understand the difference between the two. So what I aim to do is I'll first just run you guys through differential equations, how to solve them mathematically. I'll do something similar for algebraic equations, and then what I want to do is explain how the two are kind of used in tandem in SCIE1000 to do this thing where we're modeling some natural phenomena using our mathematical equations, okay? All right, so first of all, differential equations, the way that they work is you'll often hear your lecturers say that a differential equation is an equation that relates some unknown function to the rate at which that unknown function changes. Okay, so that's a bit of a mouthful, but mathematically what this looks like is, say we've got some unknown function f of x, and we've got its first derivative here, written f dash x, and just note that this is called Lagrange's notation, and the same function here, or equation rather, can be written in this way, dy dx equals to rah rah rah. This is called Leibniz's notation, same equation. So this is our differential equation. And the way that we would solve this guy is we're looking to find the unknown function which solves this, okay? So I've kind of given it away that the solutions to differential equations are functions. Now, before class, I've actually already gone ahead and solved this one for you guys because it's not expected that you guys will be able to solve these equations, but you should be able to identify a solution. And the way that we would do that is we take this guy, which is the answer or an answer. And I should also note that there can actually be many solutions, more than one solution to a differential equation, but this is one. And what we would do is we would take it and we'd substitute it into here, substitute its first derivative onto the other side, make sure that the two sides match, and then we know that we've got a solution, okay? Now for algebraic equations, they're a bit different, right? So their solutions aren't functions like the differential equations. And how we know this? Well, take this function, okay? We've got x squared plus 3x plus 2 equals 0. Now if we factorize this as such, we can quite easily see that our solutions are x equals -1 or -2. And the point being that our solutions are in fact numbers, not functions like we did up here, okay? So what does this mean? How do we use this information in SCIE1000? Well, say we've got some sort of unknown function, and let's say that that's representing the size of some fox population, right? Now, say the goal is we want to just be able to come up with some fancy function where if we plug in, now in this example, we plug in the years after 2020, it's going to spit out some number y, which is indeed the size of the fox population. Now we can't always just go straight to this step, okay? We can't just come up with a function like off the bat. It would be good, but we can't always in science, okay? But one example would be, say we knew something about this fox population. Say we knew that it was expected to increase roughly 1% per year of its original value, okay? What we then know then is that its rate of change is sort of proportional or equal to 1% of the current value or its original value, right? That information is contained in this differential equation, all right? And so then what we'd want to do is solve it. Like I've said earlier, this is the solution. And then what we have just done is we've obtained the algebraic equation where we can stick in real measurable quantities. And in this case, we're sticking in the years after 2020. We're able to plug it into this function and spit out some number, which is going to give us the size of the fox population after X years after 2020. Okay, so that's what it's useful for. Yeah, that's all I wanted to say. Thank you guys.